Hey there. Now for going on, I just wanted to point out yet another mistake in my continuous stream of mistakes. I think I had the letter S here last time, but it should have been the math value. And actually, I never ran this program to see that it worked. One thing I did was I added some sleeps here because the time was coming back to 0. Take those away. Obviously, there's not going to be any time elapsed between these resets and this printout. Nothing that this kind of counter could pick up. It's possible to make a much more sensitive ticker type thing. Yeah, so the time ends up being 0. That's what actually no, 31 and 0. So this one was a little bit. There was a little elapsed time for the first one. I can make that more pronounced by putting some sleeping. That's interesting that there was a little bit. And now the second one has come. Now that seems impossible. It's rampant. Oh, the second one. I'm going through the loop. Oh yeah, the second one gets printed out later. So some time, any time that would get picked up by such a crude timer would have to do with input and output. Writing to a device or something can actually take some amount of computing time. Noticeable as far as the machine can tell. Now, since I'm going to talk a bit about those hashing functions, I thought I'd have a look around and see, because the hash function is obviously a very important element of in computing. You saw all that theory stuff on Wikipedia, you know. I figured Microsoft's probably been doing a lot of work, getting their hash functions right and streamlining them and making them as efficient as possible. But well, internet is so slow. That it's a hash function or a hash routine or something. Oh yeah. Lots of this, certainly lots of theory on it, and it's used in cryptography and all over the place. So what I did was I just did a text search for that the function, all of Microsoft's things that use a hashing algorithm, at least that I know of, give the function the same name. It's called hash key or something. Like hash key, yeah. So yeah, lots of documentation here. Anyway, I had a look, and I discovered at least that there are certainly others that aren't there. 13 different hash functions and their implementations in the source directory. So now might be a good time for you to get out a pen and paper and get ready to have a look at the variety of different implementations of hash functions that occur in the world. You know, I mean, 13 is not that much, but you know, it'll give you a starting point when you're trying to design your own hashing function. You know, you can use, perhaps use some of these as a basis for your own design decisions. So I'll just do the search again, hash key, case word. Actually, they're all still loaded up here. We should find the same 13 anymore. I might have missed one. I didn't, mine's not called hash key, I renamed it. I had a few silly ideas of my own, and you know, so I invented, I made it a parameter that you can pass in, you know, a hash function. Okay, so now let's have a look at some of these hash functions. Now remember that what a hash function's job is to do is to take data, sometimes a variable length or a one type, and to return something usually smaller and fixed length. This isn't a fixed length thing, but we can guess it. I have a guess as to why why it works this way. Okay, now here's one, CMap pointer. Now that one does, okay, well that one divides the key value by 16. Okay, so take note of that. That's one way to do it. Okay, okay, here's a new one in CMap pointer to word hash key. And here what they're doing is they're dividing the number by 16. So that's another method they've come up with Microsoft. Okay, now here's another one. Now this is one that takes a string value. And what it does is, after validating and whatnot, it walks through the string, starting with h hash equals 0, and then shifting h hash by 5, and adding that to itself, and then adding that to the next character, and then incrementing the character and walking through the string. So that's yet another method. And this is one that uses a variable length type input. Okay, so that's how many have we done? Like 4 already? Okay, and now here's another one for CMap string to pointer, also taking a string. Now this one here walks through the string until it's null, starting with something called h hash setting to 0, and shift it by 5, add it to itself, and plus the character, the next character, until the end. That's another way, another type of, I don't know how they came up with all these different methods. It's fantastic. The creativity it just kind of blows you away. And here's another one, taking a variable length argument value. Now here they start h hash with equal to 0, And now walk through the string while it's, until I get to the end. Shift it, again shifting it left by 5, add that to itself, plus the character, the increment character. It's fantastic. It's really, like why they've chosen this particular one rather than one of the others. It's a mystery, I don't know what kind of studies they've done, what. Okay, now here's another one. So this takes a word value. This one, they divide the number by 16. So that's and they call this a identity hash for some reason. It works best for most primitive values. Okay. And here's another one, or have I hit the top? Oh no, still more to go. Now this one here takes the key value and divides that by 16, and then return that division. This is an identity type hash. It works for most primitive values. It's quite interesting, the plethora of ideas that they've come up with over at Microsoft. And then now we're into variance and calm and stuff. So we can actually see these implementations. I can't imagine what they might be after what we've seen. But a couple of them are actually implemented here. Case R4 here, where the var float value is, what they've done is they're dividing it by 16 and then returning that. And again here, another way, divide it by 16. Why this case is different from this, don't ask me. Now, was that the same function, or no, I've jumped only 3 lines ahead. No, I haven't. Yeah, I have. This is the same thing. No, this is a different one. Oh no, I missed this one here. Where what they're doing here is divided by 16, and we'll leave our one. Now we're in a different one, definitely. Now some more interesting concepts here. Division by 16. Another this double divided by 16, and here we got a date which we divide by 16. It just goes on and on. So I hope that you're getting an idea of the variety of. Oh, now here's another one, which takes a com B string type thing. Now that's this has to do with com. It's a kind of string that you can, I guess, you can pass from one process to another. They're going through a loop here, starting with something called n hash equal to 0, and I set that equal to itself, shift it up 5, plus itself again, and then plus the value of the character, which then is incremented. Fantastic. I mean, whoops, oh no, I pressed F5. I lost it. I mean, there were, you can have a look for yourself. I've lost the font. Oh, here they are, still there. Okay. Let's see what else we got. Here's another one. So I guess, okay, I can't maintain this joke any longer. They got two algorithms that they use for their hashing, and here it is. If I hit the top, no. So this is another repeat. Now, I don't think there's anything special about those algorithms. For one thing, I think there's a lot of copy and pasting has gone on here. Because as I was copying these different functions out of the various files that they were in, I noticed they were all occurring on line 42. Okay, this is on line 42 of this file. Again, line 42. Now, how much you want to bet? Where's the last one? That the above lines are identical. This one and this one. Okay. Can you say copy and paste? I thought so. These people actually get paid money to do this. Wait a minute. There we go. From line 42 upwards, it's the same. Here's another line 42 one. And it's funny that this one's on line 42 and this is the string one. Okay, now enough of jokes. Well, it might be there might be a job in determining a hash function that's good, but all evidence points to just whatever floats your boat. Do that, and it's going to be okay. And I have some evidence to support that. Now, is this the one? This is the one where I was getting messed up. Okay, is this it? Okay, now here, this is where we're doing our special struct thing. So that worked fine. And I'm really glad now that I have a map class, because these maps are quite efficient, as you'll see in a minute. Now, in one of the experiments, I wanted to find out, first off, when I was still concerned about hash functions, I'm not anymore. Actually, you could return the same number all the time, and the map class will work. It may not go very quickly, but bucket and bucket hash and hash int number do not uniquely identify an item in a map. They may, but they don't have to. You can have all numbers the same. And to prove that, I made the hash function return the same value all the time. And it worked perfectly fine. And that was with the last experiment, where, as you saw, the bucket was the same and the hash number was the same already. No, almost the same. The hash number and bucket for one of the items was the same, but not the same as another item. What I did was make it the same for all items, and it still works. And if you follow through the code, you'll see why. It has, in order to find a match, the hash, bucket number, and the local hash number with the second number, all those are things to help speed up the search. They don't identify anything. They're just a thing to help speed things up. Okay, I'll have to explain this program first. Some weird books. Now, first off, trying to be a good person and actually write a hash function instead of just copying divide by 16. I wanted my map, and I will want my map for my program. Oh, that's another thing, by the way. The day changed, so I have a snapshot. Let me just show you quickly. This in the right setting. The differences for when the week flipped, and it's still showing only that one because I haven't fixed that other problem. But we have a look at it. When the week changed to 8, how big is this? Oh, this has to be bigger. I can't see them all. They're all different, of course, because the week number changed. Okay, that's the start. But it's interesting to see what gets reset. So the week went up. All these were negative, so they were reset to 0. So only none of the earlier, what I call previous session data has changed. Only a new one was added for this one. Right? It could be that that's a D word. I could take a difference of the whole thing. But anyway, they both changed. These are the changes. That's for regedit. For this auto-generated thing, week, of course. In use, for what I've been calling in use, which I don't think, no, is in use. This became a -1. That's weird. I would have thought it would go from 1 to 0. That would be for this one, the first week 8. That's this unknown thing. No, there's no -1s in there. Oh, could be the. It's in use. Okay, doing the wrong one. Should be week 7. There's no -1. Yeah. Not sure. But anyway, so that's something of interest to look at later. At least now I'm not going to lose those things if they're there. Alright, so now it would be pointless to use the divide by 16 hashing function because here's what I call the identity hash 32. all of these hash functions have to return a D-word value. There's no Q words. Even if the key type is a Q word, it could be a string, right? But the thing returned has to be a D-word value. Well, taking a 64-bit number and dividing it by 4 and casting that as a D-word has a good chance of not producing any variation in the output, right? So I came up with this algorithm. You're seeing your very first non divide by 4 or like the string hash function. Enjoy it while it lasts. The reason this is 37 is what I want to do is I want to take low D word plus high D word and add those two together, right? And then do the divide by 16 thing, because that seems to be the standard, but now I don't think I need to. But then divide by another 2 because I've got 2 of these. So this would be 32 plus 4 plus 1 is 37. And for this one, it would be 4 plus 1, which is 5. So it's like taking 1/2 high plus low, right? This is the null version of the 64-bit hash algorithm, which doesn't do any dividing by 4, but returns something which may vary when a Q-word value varies. Like the ones in the user assist thing. This better not take a long time. Yes, it's taking a long time. Those ones change by lucky coincidence somewhere in the middle. So part of, if you took either the high or the low D word, you would see changes. I've got to find out what this is. One of the things I was thinking of doing was, I have all these extra users on my machine, and whenever I log in as a different user, everything runs so fast. So I was thinking of just dumping this user and I'm going to start using one of the other ones. This is ground to a halt now. It's too much junk is installed. The caches are now a detriment, right? A cache is supposed to speed things up, but it's how do they call it? There's the law of diminishing returns. It's at a certain point, there's so much cache data that it's faster to not use a cache. And a smart system would destroy a cache that has become so large that it's causing something like this to happen. And I can't look and see. Maybe I can control C this. No. In any event, if that ever shows up, you can see those keys. You saw them before. I could imagine if you had a big 64-bit value, it might be that only the lower D word tends to change. Or it might be the opposite, that only the higher D word tends to change. And but what you really want is a mixture of the two. Just like that string thing, right? What I could do is run their string algorithm on it. Right? I could take these numbers and just treat it as a string and run that silly string algorithm. But in general, I might as well have something for the Q words. Okay, now the experiment. What I did was, first let me try, let's not do this. And let me just declare this. I'm not using the null, I'll use the analog of the identity for 64-bit. That's just a parameter I can pass in. Now I have a tick counter. I go through a loop, number of times being the number of elements in this array, which I would like to make a small number at first. Let's go down to 5,000. Yeah, dear. 50,000. Well, that's okay, but this is going to be instant anyway. Let's comment that away for a minute. Here I've got this all set up for 50,000, units of 50,000. So let me change that. Okay. How can I generalize this? I can't in the message. How about this? Do the same here. If percent 500 equals 9, the lookup time for the last 500 entries is such and so. That's what I want to print out. So I'm going through and I'm adding, which is a pretty wide range of numbers, and creating a string which contains the random number generated. Doing this printout, adding it to the map, and incrementing numbers used for index. Index being this. Maybe it's better if I just run it. You'll see. I want to get an idea of how this thing behaves when you add more and more items. And does the hashing function, if I alter it, can I change the behavior in any significant way? And I found so far for the second question, not really. It's the speed of adding and retrieving and removing items is not very sensitive to the hashing algorithm. Almost any algorithm is going to put things fairly smoothly into the buckets, I guess. Okay, so if I run this, Let's say, now it went so quick. Okay, these times are 0. So let's increase this to 50,000. Okay. So now I'm adding 50,000 randomly generated numbers. The value type is a string, and the string also contains the index. So okay, it's slowing down now. So now this is for every 5,000 assignments, it's printing out how long has elapsed, how much time has elapsed. Okay, now it's deleting things or looking up. No, it's just looking up. You'll notice it went faster and faster. Just a minute. Now look at the code. What is this second part doing? It's just doing a lookup using the index numbers that were generated when I was adding them. Okay. Now this index here is an increasing number, right? And here I'm walking through using the same index. Well, so I'm not printing out what the value is. I should. This lookup would be a lookup for like the first items that I added, right? And these lookups would be for the last items that I added. So lookups for things recently added is quick, and things added long ago is slow. And you know that has to be true, because when you add something, especially if the buckets are all full, and it would be in this case, rung 17, and there are a lot of items, a new item puts itself at the head into the bucket list, and the older items are pushed further down the linked list, right? If I increase the buckets, now that's what I got this for. I choose a prime number, because I think you're probably supposed to use a prime. And I got a whole list of prime. I downloaded. 10,000 prime. So let me try, instead of 17, we'll try, I think 257 is a good number actually, because it's one more than a power of 2. I think that's a good rule of thumb. Those are special primes, I think called Mersenne primes or something, and they have magic properties. That one. So now I'm just increasing the size of the table. Now you'll notice that it's much faster. The lookup time, the assignment time is slowing down, and the amount of slowdown appears to be linearly increasing, right? going up by a very small amount, but it is quite a bit quicker, and I don't think making this any bigger is going to make it any more quick. Like, I don't know if I can find another magic one. 1025? No, 20. Well, this is close to one of those. Here's a huge bucket list, 1,000 buckets. But I don't think we're going to gain anything. We might even lose. Well, we'll probably lose. It's a little bit, no, it's faster, definitely. No? See, now with that many buckets and 50,000 items, yeah, 50,000 items and 1,000 buckets, so that's an average of 50 items per bucket, which isn't too bad. It gets more interesting when you really muck this up more. Print out every 50,000. I'll print out after I've read 50,000 items. This is what I originally had. And let me just turn this off first. So by default, with only 17 buckets, if I'm going to add 50,000 items, no, sorry, 500,000, 500,000 items, you're going to see that that it's going to be very, very slow and increasingly slow as the items accumulate. It might be maybe 10-15 seconds before we see the first report. I guess I could have increased the report. Yeah, report density is too low. No, I can't do that. Let's do this. We'll keep it at 5,000. Because it's just too. Without the recorder running, I do see a couple reports before I give up on it. But with the recorder running, God knows how long it would take. And I can fiddle with that hashing algorithm, but it's really 5,000. Okay. Now, you see, this is not linear. Now it's adding like seconds. First it was adding less than seconds, and this is going to go up. The differences are increasing. That's nearly 1.3. Well, that's 1 second. More time. It's quite slow. Now remember, there are 500,000, so we would be waiting a long time for this to complete. I'd like to put it back to 50,000. So I print out every 50,000 assignments and whatevers, but I'm going to bump up the size of the buckets. Now it should be, we should see some reports with this many buckets. 17 is just too small for 500,000 items, right? All it is a link, a single linked list. Okay, so we saw one, 4 seconds, and it's only growing by about a second, but the time is growing in an apparent linear way. So the more items there are, the longer it takes to add items. We're adding the same number of items, but it takes longer. Now, why would it take longer? Probably because we're getting, well, those linked lists are long, right? If we add more buckets, the time is just going to get faster. Let's say we bump it up to like 7,000 buckets. It means that the linked lists aren't as deep on average, right? And that there's a better chance to get for a miss. Now that's not too bad. Yeah, I wonder if we can get even better speed. I'd like it so that the what you want is, I think, that the linked lists, the size of each bucket should be below some minimum value to get up the optimal speed. Now it didn't help, right? It seems the best we can get is about 3. But it's not, it didn't grow though between those two. Well, that did though. It's not growing very quickly. That's almost the same time. That was a decrease in time. It found some empty spots. So the growth in time is nearly 0 here. It's hanging at around 4 seconds per 50,000 assignments. It actually went through the whole cycle. 500,000. That's 500,000 assignments, including all the allocations and everything, right? And within that short amount of time. So these maps are quite fast if they're initialized, if you're using a good size bucket size. Do I really need it to be that big? What if I took 10, 15,000? I think that was probably optimal. If you keep going up it, like I have an experiment down here. Well, let's watch this one. Same thing. The first one's always about 3.5 seconds. Like that, no, seeing this is just as good so far. It's not, the time is not increasing. It's constant. Now I know that the table's got to be full, right? It's a 500,000 things in a way of some tens of thousands of buckets. But that was as fast as the last one. So that's the balancing act. Here's one example. I used a 5,000. See, these are the times I get without the recorder. 5,000 buckets. The growth is smooth for this one. Could be just luck. And now this one, using the null hash, I wanted to see if the hash function had an effect. Well, it might have. There's a big jump here, but it could have been random, right? I have to try more experiments. And then this happened. I reduced the buckets to a smaller number, and I must have found a good match between buckets and what is it? What has to go into what? The hashing number that's returned should optimally spread evenly into the buckets, and this must have spread really evenly into the buckets, because look at these times, comparing with these. So anyway, that's just fiddling around. The point is, it's understood, the whole thing is understood, and I have a class now, an associative array class, and I can use keywords, which I want for my thing. I'm going to put all those things now, the things as I read them. I'll read them on the fly instead of going through the whole list, right? If I select a different thing, I'll load it up, and I'll have a map of file time versus this structure, which is becoming kind of an interesting little thing to look at. I'm very curious about the things that got reset. Yeah, okay, max. All the session indices go up. Is there anything of particular interest? Which one is in use? I think that's UNC. Where's that? In use. See that anywhere? First launch time. In use. It's a bool. Bool? No, so that's just a name. That's the thing that just immediately follows the counter in string. So that's not this last thing. The counter comes just before the time. Find something with time. Here's one with time. That's this one. In use. Pre-make downloader. Where is it? It's here. It wouldn't be for this one though. It would be either this or this. Huh? Oh, these are the differences. Right. What's this big difference? Oh, that's it. No, that's weird. What is that? That's a negative number. But it's a difference. Sorry. My fault. Sorry. I keep forgetting. Anyway, I'm gonna have a look at and try to see if I can learn anything from this. And I've got to get it indicated visually on the thing here. This is completely useless until I can see like little red up and down arrows. So that's the next thing I'm going to do. And now I got my map. I got all sorts of tools I can use. So it's just a little addendum. See you.